Hi everyone, my name is Manon Blanke and in this video I will show you my research project that I executed to conclude my master in Game and Media Technology at Utrecht University. During this video, I will first go over some core concepts and ideas before explaining how I was able to make ray-based rendering faster and why this is useful. I did this project in the field of computer graphics, where I studied how we can further accelerate rendering by combining two existing techniques in a novel way. Rendering is the process of generating an image from a 3D model by means of a computer program. We do this for movies or for games whenever we use computer animation and we need to produce an actual image from the models we created. During the rendering process, it is determined what the final image should look like by calculating how the objects in the scene are positioned relative to each other and how they should be lit. For movies, every frame needs to be rendered only once, and once this is done, we put the frames together to create a final movie. For games, however, the scene can change completely with every button click, and thus we need to render a frame in a matter of milliseconds, so that the user does not experience lagging. So, rendering needs to be fast. Therefore, games often use a rendering technique called rasterization, in which lighting effects are approximated. It is super fast, but this technique is not able to accurately visualize shadows, reflections, and refractions. This can be done with another technique called ray tracing, which is a physically based technique that simulates the physical behavior of light. This is very computationally expensive, which is why it is not used that widely yet in games. And that is a shame because it allows us to produce highly realistic images. So, because the images we can generate with ray tracing look so much nicer than with rasterization, we would like to be able to use this rendering technique all the time. Therefore, a lot of research is being done to make ray tracing faster, so that more applications can make use of this technique. My research aims to do so by combining two existing techniques, bounding volume hierarchies and foveated ray tracing. I will first go over these techniques before explaining what I did exactly. The use of bounding volume hierarchies, or BVH for short, is a popular acceleration technique. The reason why ray tracing is so computationally expensive is because we need to trace a light ray through each pixel, and for that light ray we need to calculate whether it has a hit with any object in the scene. This intersection test between a ray and an object takes quite some time, and we need to do this for every pixel and every object. For a model consisting of 100,000 primitive objects, which is quite small for a model, rendered on a high-definition screen, this already requires billions of calculations. And actually we need to trace multiple rays through each pixel, because else we get a very noisy image. If we could reduce the number of intersection tests, that would save us a lot of time. Bounding volume hierarchies is a way to do so. Instead of testing for an intersection between a ray and every object in the scene, we put the objects into boxes. These boxes together form a hierarchical tree, where each box consists of two smaller boxes, and those boxes again consist of two smaller boxes. The smallest boxes contain the final primitive objects of the model. If we find a ray that does not intersect a large box, then it surely also will not intersect a smaller box, so we do not need to test for that. This way, we can greatly reduce the number of intersections, and that makes this acceleration technique so popular. The question is of course how we construct these boxes. We do this using a top-down approach. That means that we generate a large box over the entire scene, and we split this box into two to create two smaller boxes, and then we split that one again until we are satisfied. But how do we split these boxes into two? Two main methods to do so are the spatial medium split and the bin surface area heuristic. The spatial medium split means that we just simply split the box right through the middle along the longest axis. This is very fast, but it does not do a great job at reducing the number of intersections. We will call this a low-quality split. A better method would be to use the bin surface area heuristic. With this method, we evaluate for different positions how putting the split plane there would reduce the number of intersections, and then we choose the position that reduces the number of intersections the most. This works great, and we refer to this as a high-quality split. It does, however, take more time because of all these evaluations we need to do. Either way, the bounding volume hierarchy that we create will greatly speed up ray tracing compared to naively testing each ray against each object. A completely different way to speed up ray tracing is foveated rendering. Foveated rendering makes use of how the human visual system actually works. When we look around us in the world, we do not see everything equally sharp. Instead, whatever is right in front of us we can see sharply, but the things in the corner of our eyes appear blurry until we move our gaze towards them. The part of our visual field where we see sharply is referred to as our foveal vision, while the blurry parts are in our peripheral vision. Typically, images are rendered with an equally high quality over the whole image, but if the image is large enough, then a large part will fall in our peripheral vision, and we cannot perceive that much detail there anyways. So foveated rendering makes use of this idea by rendering that part of the image where a user is looking at with a high quality and the other parts with a low quality, because we cannot perceive this quality difference anyways. For ray tracing, foveated rendering means that we send more rays through the foveal part of the image to produce a sharp image there, and few rays through the peripheral part of the image, where we can get away with a noisy image. So far, these two techniques, bounding volume hierarchies and foveated rendering, have existed side by side, separately. But sometimes 1 plus 1 is more than 2. So, for my research, I studied whether we can combine these two techniques. I studied whether we can adapt a bounding volume hierarchy to foveated ray tracing to generate our images even faster. And the faster we can generate these images, the more attractive it will be for game developers to use ray tracing in their games to create even better looking graphics. This image generation speed is measured by the total time to image. The total time to image is a sum of the construction time of the BVH and the actual rendering time. Why should this work? Well, recall that we got these two BVH construction methods, a low quality one that is fast but does not reduce rendering time a lot, and a high quality one that takes more time but does a better job at reducing rendering time. If we barely trace any rays through the BVH, we would not want to waste our time at building a high quality BVH, because the extra time spent on construction would not be paid off in terms of saved rendering time. If on the other hand we would trace billions of rays through it, and a high quality BVH would make each ray traverse through it even just a millisecond faster, then it definitely would be worth it to spend an extra second of our time on construction. Recall that for foveated ray tracing, we would like to trace many rays through the foveal part of the image and a few rays through the peripheral part. So this is the plan. Before rendering, we construct an adaptive quality BVH. This BVH is of a high quality around the part of the model inside the foveal region and a low quality around the part of the model inside the peripheral region. The total time to image, construction time plus rendering time, should be lower than if we were to make the whole BVH of either a high or a low quality. And it turns out that we can actually do this, so the adaptive BVH is successful in reducing the total time. This is great news for game developers for mainly wide field of view displays, such as virtual reality games, where many pixels will lie inside the peripheral region, where we can reduce image quality. By incorporating an eye tracker in the VR headset, we can know where the user is looking, and thus what is inside their foveal vision and what is not. My implementation of the adaptive BVH, which was tested on a laptop device rather than a VR device due to practical constraints, needs to be further developed before it can be used for this specific purpose, but the first results are promising. So how did I develop the adaptive BVH exactly? First, I built a foveated ray tracing functionality into an existing ray tracing system. This foveated ray tracer defines a foveal region on the screen, and depending on the position of the pixels relative to this, we trace more or less rays through it. As a default, I trace a single ray through each pixel in the periphery and 16 rays through each pixel inside the foveal region. In the part here, that represents the region of our visual system where visual acuity declines, we gradually decrease the number of rays per pixel. For the dragon scene, that would look like this. Here you see a full render of the scene. Here we rendered the same scene with foveation, where the inner radius of the fovea is equal to the outer radius, so that there is a hard boundary fovea. You can clearly see the difference in quality between the foveal region and the peripheral region. If we use the foveal vowel function, the render looks like this. Now there's a smooth transition from the fovea to the periphery. We would like to build a high quality BVH around the part of the model inside the fovea and a low quality BVH around the other parts of the model. Now it is easy to see which part of the model lies in which region, but for the adaptive BVH builder, we need to know this during construction of the BVH, so before we actually render the image. We cannot know for sure until we actually render it, but it is possible to make a prediction about this. I tried 4 different tests to predict during construction which boxes of the BVH lie in which region. These are the foveal density prediction tests. 2 of these tests are based on projection and 2 are based on intersection. Both tests based on projection and both based on intersection have a simple version and an extended version. Projection is the process of mapping a 3D point on a 2D surface, in this case the screen. The simple projection test is center projection, where I projected the center of the BVH box on the screen and check if it is inside the foveal region. Its extended version is called extended box projection, and here I projected all 8 corners of the box on the screen, generated a circle around these, and checked if there was an overlap between the circle and the foveal region. On the other side, we got 2 tests based on ray box intersection. Intersection is the process of checking whether a ray hits an object in a 3D world. For the simple intersection test, I trace a single ray through the center of the fovea, and if it has a hit with the BVH box, I would classify that box as being inside the foveal region, and else not. The extended box intersection test traces 32 rays spread randomly throughout the foveal region and tests if there is any hit with the box at all. Based on the outcome of this test, we split the box using a high quality if we predict that the box is lying inside the foveal region, and with a low quality if we think that the box lies in the peripheral region. Which of these so-called foveal density prediction tests perform the best depends on the scene. I tested the algorithm on 3 different scenes: a dragon, a lumberyard bistro scene, and a model of a power plant. For each scene, a different test turned out to be the absolute best one. In these bar graphs, you see the performance of the uniform low-quality tree and the uniform high-quality tree on the left side in orange and yellow, and the performance of the adaptive quality tree using any of the 4 foveal density prediction tests on the right in green. The performance is measured as the total time to image, shown on the y-axis. For the dragon model, multiple foveal density prediction tests allow the adaptive BVH builder to produce a lower total time to image than building a full low-quality tree or high-quality tree. The absolute best performance is achieved by using the center projection test. For the lumberyard bistro scene, this is the ray box intersection test. And for the power plant model, it is the extended box intersection test that yields the lowest total time to image. The extended box projection test turned out to be the second best for each scene. It is able to reduce the rendering time the most out of all tests, but suffers from a long construction time. If we could reduce that, then this test would perhaps be the best one overall. The success of the adaptive BVH builder also shows to be robust against changes in the settings of the fovea. For example, we could increase the size of the fovea or tune the difference in quality between the peripheral part and the foveal part of the image. I tested the adaptive BVH builder for different sizes and sampling densities, but in each case it was able to outperform the standard build methods. The adaptive BVH builder is not perfect, however. For starters, it requires an initial balance between the construction time of the BVH and the rendering time. If the rendering time is too large in comparison to the construction time, for example when the screen resolution is large, then it will be hard for the adaptive builder to outperform the overall high-quality tree because it could never render as fast as the high-quality tree. Also, because this combination of methods is so new, I really tried to stick with the basis and test several core assumptions. However, this means that the current implementation of the adaptive BVH does not compare to what we would like to see in a real state-of-the-art rendering system. For example, it does not do full shading of the model, as only primary rays are traced. It runs on a CPU instead of the GPU, and it is not fully optimized. Furthermore, the algorithm does not work yet for dynamic scenes and dynamic foveas, in which case we would want to update or restructure the BVH rather than fully rebuilding it. So, a lot of work remains to be done to generalize the adaptive BVH to incorporate state-of-the-art techniques. It would also be interesting to incorporate multiple build methods in a more complex and interactive way, rather than making a binary decision to use one of the 2 available ones, as it is now. Furthermore, it needs to be verified whether this approach actually works for virtual reality scenarios, where the number of rays that needs to be traced through the periphery is way higher than on a laptop screen, and there will be additional issue of dealing with system latency. But the first results are promising, and I'm looking forward to see what will come from this. Thank you so much for watching this video. Should you have any further questions, feel free to contact me, and enjoy the rest of your day.